Thanks very much, everyone, for being here. So as Boppy mentioned, my name is Alon. I'm the co-founder and CEO of Blue Cheetah Analog Design. But for this talk, I'll really be wearing a sort of ODSA, OCP hat, and I'm really representing the efforts of the overall ODSA, essentially bunch of wires working groups. So hopefully many of you who are here have heard lots about bunch of wires already. And this has been an effort that's been around for probably about almost 4 years now. And essentially this is really an open PHY and link layer really group of specifications, particularly for die-to-die parallel interfaces. And really obviously focusing heavily on this whole chiplet sort of approach and economy that we're all talking about here. So, I won't actually spend a lot of time in low-level technical detail, but, let me assure you that all the technical metrics and everything are state-of-the-art, much like, many other approaches that, people have been proposing, so up to 32 gigabits per second per line, sub half picojoule per bit, less than 8 nanoseconds bus-to-bus latency. I'll say some more about that in a little bit. But yeah, overall, it is very much, as far as we can tell, one of the most energy efficient and essentially overall low latency approaches that are out there. And the specification is indeed compatible with a very wide range of packages, IC technologies, and cost performance, let's say design priorities. And again, I'll sort of say a little bit more about that in a moment. But really kind of the key philosophy and idea behind the bunch of wire specification is to enable the die-to-die interfaces to actually be customized to their host chiplet products. And I think an important point that I'll be touching on a couple times here is that, at the end of the day, chiplets were being brought about all because of essentially semiconductor manufacturing cost. And so what we need to keep in mind, therefore, is that it's not just the fact that we've now broken things up that magically makes everything interoperable. It's really that we took this whole approach to try and reduce the cost, and so we better make sure that whatever actually interfaces and things that we're trying to insert into here allow us to retain the types of specializations and customizations people would be doing to get their product cost to actually be sufficiently low. So because of that, the spec itself was very much architected to be essentially as minimalist as possible in the features that are required, but still support interoperability and the overall benefits of standardization by essentially sort of figuring out what really are the minimum sets of things that we do need to either require or essentially provide these specifications on, but allow people the flexibility to be able to essentially work inside of that specification architecture to tailor to the specific product needs that they may have. So just from a basic organizational perspective, this is electrically speaking, a parallel interface. So the basic unit element is what we refer to as a slice. It has 16 data wires. It has a source synchronous differential clock. There's 2 additional optional wires for essentially peripheral functionality like forward error correction or data bus inversion, things of that nature. In fact, there's actually other, let's say, logical definitions that we've come up with in the meantime. So things like, by 8 and so on and so forth. But the basic unit element is essentially this group of parallel wires with a forwarded differential clock. So again, continuing on this theme of allowing people to essentially make design trade-offs to meet their specific, essentially, product needs, there's a so-called stack depth, which is just how many of these unit element slices we essentially stack down in the orthogonal direction from the die edge. And the idea here is, of course, that you can essentially increase your overall shoreline bandwidth density by increasing that stack depth, obviously at some cost in packaging either layer count or complexity or et cetera. So what this means is that products designed around a bunch of wires can span anywhere from the absolute lowest cost or simplest sort of at least existing today types of manufacturing, where you may have like a 1-to-1 organic laminate sort of stack up, all the way to sort of the most advanced silicon interposer or bridge types of technologies. And then finally, a so-called link, that's just sort of a logical unit element that interfaces with the sort of on-die bus ports, sort of again as a single logical unit. So essentially from a basic, on the link layer side of things, which is, the thing that acts as the interface between the raw PHY itself and, of course, the on-die buses that you're trying to export. The whole point here is very much, as was described in a couple of the talks, where you're just trying to do is create the illusion from the individual chiplets perspective that they really are connected onto, they're really all sitting monolithically on the same die, when in reality they're actually disaggregated into multiple different dies. So essentially, the link layer is just the one that's providing that seamless transport of whatever the on-die bus protocol is over the die-to-die PHY raw bandwidth itself. So here within the link layer, sort of an important point is that there's a layered approach that's taken, very much to allow, once again, the configuration flexibility as well as the interoperability that we're looking for here. So essentially, there's a core link layer itself that has a certain packet format definition. It has a certain set of functionality to like quantization, error protection, and so on and so forth. And essentially, between the link layer and any individual bus protocol, there's a so-called transaction layer, where that transaction layer is the one that then is mapping the individual, essentially, bus protocols you're communicating with, really the ports of the bus protocols, onto the individual substreams that are created by that lower level link layer. So I just wanted to walk through a few examples of essentially how both interoperability and flexibility can actually be supported. So the first examples, I'll just focus on the PHY side of things. So the specification itself only requires the ordering of wires on the package, not actually like very specific individual bump maps. The idea there being that people may have various reasons that they need to use differing bump maps, but you still want to sort of explain and ensure that people actually in a compatible ecosystem would be able to communicate with each other. And it turns out that just by specifying the wire order on the package, you can indeed support that. Similarly, there's some applications where you know very well what the clocks on every side will be, and so therefore you don't actually have to sort of enforce more complex clock domain crossing structures, and so only serialization, deserialization is the real requirement inside of the PHY itself. Similarly, and arguably maybe even more importantly from a system design perspective, there's two key concepts that are captured in these specifications that allow people to actually tailor the individual buses and protocols that they use to then communicate from one chiplet to the other. So in particular, an interface profile specifies, okay, what are the actual bus protocols that a given essentially die-to-die interface is talking to? So for example, something like AMBA CHI or AMBA AXI, so on and so forth, or combinations thereof. And the idea there is that you can again specify that in a flexible way by saying, hey, my chiplet has these specific buses that it's using, and therefore if you want to interoperate with me, you need to essentially follow those same buses and those same protocols to communicate with that chiplet. Similarly, even when we say that we're following a particular protocol, as we all know, these protocols were built in a powerful way that allows a lot of flexibility and customization, right? Variable data widths, various fields, various optionalities that again, SoC designers are used to exploiting in order to be able to optimize the performance, cost, and efficiency of their own individual products. So just like that flexibility exists on the SoC, that flexibility needs to be reflected and handled in the specification as well. So in this case, there's a so-called bus variant that, again, it's just saying, okay, within a particular protocol, what are the actual fields, what are the actual widths, what is the actual packing that we're using to make these things actually sort of match with the particular design of the chiplets that we're looking at. So there's a large amount of collateral that's been developed over the years, essentially to support, how one would do these designs with bunch of wires, sort of as the specification, including lots of detailed requirements on the electrical and timing design side of things for the PHYs themselves, as well as a lot of work that was done in signal integrity, package designs, and so on and so forth, and all of that is publicly available today. So I am happy to say that there are quite a large number of silicon demonstrations of bunch of wires, for example, at 16 gigabits per second. In fact, actually even beyond that already today. You can basically walk next door and you'll see a few of those sort of live. This is by no means a complete set, but just as a couple of representative examples, since I'm here on the podium, one of them will of course be from Cheetah. So that's in a 12 nanometer TSMC technology. Again, we've got the demo, just come check us out. As well as actually D-Matrix, they have a demonstration they've done in TSMC 6 nanometer that again, you can just go check out the booth next door. So much of the power, obviously, of a standard is to try and make it so that there's a wide variety of essentially IP vendors that are out there and supplying things to essentially meeting the specifications here. With the idea being that if the specification has done a good job, you should be able to get multi-vendor interoperability as well. And so I think, as was mentioned previously, right, you're never really going to have a true plug fest, right? This is not, PCIe kind of thing where you just plug in a cable and there's a big PCB on each side, right? This is actually something where have to really build kind of fairly customized hardware to demonstrate the interoperability. And indeed, there's a community-driven and sponsored effort to demonstrate that multi-vendor interoperability, specifically in this case between Cheetah and D-Matrix. This is an example of sort of the package design that's being developed here. And so again, this is just sort of showing that indeed there's life and legs in essentially getting these things to talk to each other. So from an adoption perspective, there's already been a number of ecosystems that have formed around bunch of wires, and it is being designed into a large number of products. Whether it's tens or hundreds, 5. Obviously, not everyone is speaking entirely publicly about what they're doing, but from my personal knowledge, it's on the order of tens of products today that are being built around this. And just to give you sort of, let's say, a sampling of that or a flavor of that, there are known PHY implementations, either announced or just sort of things that people are known to be working on in 65 nanometer, 22 nanometer, 16 nanometer, 12 nanometer, 7, 6, 5, 4, and 3. So there's quite a bit of design activity that definitely has already happened here. And as I said, there's a number of demos you can go check out on the floor. So I'm just going to quickly kind of wrap up, mostly speaking with some thoughts a little bit moving forward, which in some senses is going to be a reminder once again that chiplets emerged as a solution to the semiconductor manufacturing cost problem, right? That was the raison d'etre for chiplets in the first place. And so if we really want to realize those cost reduction goals, it's almost always the case, particularly in our experience, that the chiplets themselves are fairly heavily tailored to the end product or product segment that they will turn out to be serving. And so that means that we really want to maintain flexibility in the definitions of the interfaces so that, again, we're not sort of having the interface force decisions onto the product that may then make it actually unsuitable for the end market application. And so again, Bunch of Wires, I think, was uniquely designed with this goal in mind of leaving that flexibility in place while allowing essentially interoperability amongst, let's say, groups of companies and groups of products that know what the particular requirements in that space actually are. So as I said, just to summarize, Bunch of Wires was really uniquely defined to allow adopters and implementers to select and trade off between varying different product level requirements without needing to switch die-to-die interface standards in order to meet their particular needs. Bunch of Wires is available now. It's being adopted by a large number of companies and sort of for their own products in various application spaces. And it is completely openly licensed, no NDA, no signature, no nothing. And it's available to anyone for adoption and participation. So I've left a few links here for sort of things you can follow up and participate further. With that, I'll thank you all very much for your attention.
Speak loud enough, I can. Oh yeah, okay, it's on now. Yeah, yeah. Thanks. Great talk. My name is Nilesh, and my question is, how does Bunch of Wires compare with UCIe, and will it be absorbed into UCIe eventually?
Yeah, so I won't make any comments, forward-looking statements or whatever. Not that I'm a CEO of a public company. No, so. There are definitely differences between the two from a kind of, let's say, detailed electrical specifications, guts of the PHY and how they work. There are certainly differences there. I would say that the biggest difference is really mostly in the target of what the specification is trying to achieve, right? And you can sort of see it, largely speaking by name, in that, UCIe is very much, sort of shooting for an ultimate plug-and-play type of approach. And the design philosophy behind it was to try and make sure that everything will plug and play together. And Bunch of Wires is really much more about, okay, hey, let's create specs that people can actually interoperate with in regions that that they have figured out for individual products, but not actually have to switch sort of specifications to get to a differing product segment. Whether or not things merge at the end of the day, different question. I think there's certainly logic behind that, but those are the, I'd say, underlying design decision or design philosophies that drove to different decisions.
Thanks.
Yeah, absolutely.
Any other question? One more over here. We heard in the UCIe about the different protocols that have been demonstrated over that PCIe, I think CXL, ARM. Can you talk a little bit about what's been demoed and what's been interfaced and translated over the BoW?
Yeah, so I'm certainly not aware of the exhaustive list, but most any of the AMBA protocols, that you can come up with, CXS, CHI, AXI, AXI Lite, ACE, all of those have essentially been implemented and transported over Bunch of Wires. I believe there's probably even some CXL implementations out there as well, but yeah.
So one question I was trying to understand. This is actually a good one. We have seen both UCIe 1.1 with the A and S, and this is the third one. So using the OCP influence, can we also work with, let's say, TSMC, Intel, or Global Foundries to make sure that each of the tech node-wise, the microbump they are using it, their height and physical interoperability, as well as the reliability point of view, to see the true you can use plug and play. Because today what happened is, right, the challenges. When we try to do something, there are a lot of physical limitations also come into place to truly use them.
Yeah, it's a great question. And I'm going to sort of answer it by not answering it, using my sort of former faculty member hat. You're absolutely correct. Those are big challenges. And in fact, I think if one really wants to create a sort of more interoperable chiplet ecosystem, in fact, if you really want to do a plug-and-play chiplet ecosystem, I think you basically need JEDEC level of specificity on each individual chiplet for not only what its functionality is, but what its electrical interfaces are, what its bump map is, what its bump technologies are, long list of other things that, like I said, in JEDEC, if you go and buy a DDR DRAM, it's that level of specificity that I think you're going to end up needing to actually make sure that there is a plug-and-play type of environment there. Having said that, I think there's another sort of interesting point that Mark Kummerly, who I hope I won't be stealing his thunder, but he made at a workshop that happened not too long ago, where especially in the advanced package technologies, reach is not something that really is available, right? In the very advanced technologies, you have very thin wires that have fairly short reach, and so a lot of the types of flexibility that otherwise you could have leveraged to make these things just work is a lot harder, right? You get a couple millimeters offset somewhere, and that could basically stop you or prevent you from really working at all. Whereas if you're in a more longer reach type of technology, whether it's organic laminate or sort of a fan-out RDL type of approach, we've got thicker metal wires. That's something where you could more feasibly imagine that conformations and slight misalignments and whatnot can actually be handled without sort of just breaking the electrical performance of the interconnect.
Yeah, thank you.
Absolutely.
All right, thanks everyone.
Great. Thank you.